יש כאן שורה של כיסאות שמגינה עליו. איזה שורה מפגר את זה. קראת המזכן?
לא יודע, זה סבוב.
עכשיו סבבה לך.
לא, זה בטוח.
מה לא?
תראי כמה רעש, איך אפשר לספור את זה?
מה, רעש זה כאילו...
רעש.
כן, בחיים. רעש.
זה התקדמות משבוע שעבר. זה התקדמות משבוע שעבר. איפה יש עוד שבוע שעבר?
שורה שלישית.
שורה שלישית. איפה זה בשבוע הבא? זה 1:30.
שאני עושה כאילו. זה לא יקרה.
מוסר פיננסי. אז אל תגידי לי. מה אחר?
אתה רואה? כאילו משהו, עכשיו אני מרגישה כאילו שיימי.
סיכוי להסתכל על יעל.
למה שיימינג? זה באופן מכוון.
Okay, good afternoon. So, today we are going to continue the last week's lecture, and I would like to show you perhaps the most amazing fact in physics that have also an interesting relationships, I think, with the capability of AI networks to imitate our language or to recognize things and so on and so forth. But let's start with, of course, we will start with technicalities. This is this course. It's about technicalities. But sometimes you find something nice in technicalities. So, what we did last time, just to remind you, we were speaking about summations of series. And first we were speaking about converging series, like 1 minus 1/2 plus 1/3 minus 1/3, 1/4, and so on, which is log 2. And we provided two methods, Shanks and Richardson, that accelerate the convergence. Now, what does it mean accelerate the convergence? You cannot accelerate the convergence because maybe the millionth term in this series is 10 to the 10 to the 10, right? I didn't write the million terms. So Shanks and Richardson accelerate the series provided that the model of the series, like something that goes up and down and the partial sums are converging, something like that, provided that the series satisfied some expectations that we have. So we start with a theory about what the series is, and then we develop a model. If the series convergence is like that, then Shanks will work quite nicely. If the series convergence is like that, then Richardson is going to work. Right? This was one part of the lecture. Then we moved on to series that do not converge, like 1 plus minus 1 plus 1 minus 1, or even 1 plus 2 plus 4 plus 8, and so on and so forth. And we discovered that these series, of course, do not converge, but we can make them converge by using Euler summation. Now what does it mean? What does it mean? We make them converge. We multiply everything by x to the n, and then we sum, right? And then we sum, then we plug x equals 1. It implies, as I tried to convince you last time, that the series is a wrong representation of a nice function, right? Like if we have the function 1 over 1 minus x, that's a great function, no problem with that. Okay, or maybe I will take 1 plus x even. So for every positive x, this is a very nice, great function, no problems with that. But it yields the series minus 1 to the power of n times x to the power of n, and if x is 5, I will get numbers that are going larger and larger, and I will have no convergence. The reason is that this is a Taylor series, and the rule about Taylor series is that they converge only on a circle. This is a Taylor series around 0. Maybe technically speaking, it's Maclaurin series, but because it's Taylor series around 0, it can converge only in the disk that is limited by the closest pole. And the closest non-analytic point is here at minus 1. So this is converge only for x equals x smaller than 1. However, this function is great. There's no problem at all, right? So we are trying to guess the function using the series, and Euler is a methodology of how to, it's a suggested methodology for doing right that, to guess the function that generates the series. You see my point? Okay. So first of all, I would like to just complete the last lecture by showing you another method to, I'm going to talk about it quite briefly. Another method to do a summation instead of Euler summation. One can try Borel summation.
נדב, אתה יכול להדליק את האור? שפה.
Okay? One can try Borel summation, and Borel summation, you remember what we did in Euler summation. In Euler summation, we have a sum over an. We replace it by sum over an x to the n, where x can be smaller than 1. Did the summation and plug x equals 1 after the summation. Right? So Borel summation is a similar trick. However, it's not as simple as that. Borel noted that the integral from 0 to infinity of e to the minus t to the n dt, what is that?
The gamma.
This is the gamma of what?
N plus 1.
Of n plus 1, which is what? N factorial, right? So 1 over n factorial is 1. Right? It's a, if you are looking for a complex way to write the number 1, okay, this is one of them. Okay? And therefore, I can write sum of an from n equals 0 to infinity. I can write it as sum from n equals 0 to infinity of an times 1. That's fair. Okay? And then I plug 1 from here. So I have sum from n equals 0 to infinity of an over n factorial, integral from 0 to infinity of e to the minus t to the n dt. Okay? Now, if now the integral converges, so I can replace, exchange the summation and the integration, and I will get the integral from 0 to infinity of e to the minus t times the sum from n equals 0 to infinity of e to the minus t, t to the n over n factorial. Where was the an? I need the an, of course. Sorry, an. dt. Okay, that's the idea of Borel. So suppose this, you can sum this, and you can plug it here, and you get the answer. Okay? Now Borel, in some cases, if you see if an is growing up exponentially, right? Then this will not converge, right? Because x is smaller than 1, but an is going exponentially. This may converge because here you have n factorial, which is going like e to the n and n. So it's so in some cases you cannot use Euler, but you can use Borel. Yes.
You can Borel the Borel?
No, this is not an accelerator. This
no,
is.
but if you have like it's convergent still, but you need to do an.
I don't think so. I never thought about it, but it should. I don't know. I guess not. So just to take an example, let's think about the series 1 minus 1 plus 1 minus 1 ta-ta-tam. That last time, so this is sum from n equals 0 to infinity of minus 1 to the power of n. And it does not converge. And now let's plug it in the Borel. So if an is minus 1 to the power of n, I will have here sum from n equals 0 to infinity of minus 1 to the power of n t to the n over n factorial. Now what is that?
Exponent.
This is of course e to the minus t. So I will have an integration from 0 to infinity of e to the minus 2t dt, which is 1/2, which is exactly what we get from Euler. Right? So this is Borel, of course. I want just to present it, that you know that there is such a thing in the world, but this is not the main topic of this lecture. Okay. Fine. So I guess that you got a message here. That there are functions, and as I say, a function is some Platonic idea that live with God in heaven. And what we see is only the ways that this function exposes itself to us. And sometimes the function fails to expose itself in all its glory, because it's 1 minus 1 plus 1 minus 1 blah 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 blah. But then we have to guess a better way to see it, and this is the Euler. Okay? Now, there is another way to try to see the function through its series, right? And this is something which is called continued functions. So I will explain to you. So we have a power series. We have a series. And we want, power series. I'm speaking about power series. And I want to represent the series by a continued function. Let's give an example, right? Suppose I have the series sum over from n equals 0 to infinity of an x to the n. I want to represent this series by a continued exponential. That is, I want to represent it by b naught e to the b1 times x, e to the b2 times x, e to the b3 times x, e to the b4 times x, and so on and so forth. You see what I'm doing? Now, what does it mean? What is this equal sign? What does that equal sign means?
Some say it converges to the same.
When, I mean, okay, this series is is characterized by A0, A1, A2, A3, and so on and so forth. Right? This series, this who knows what, monster, this monster is characterized by what?
B0.
B0, B1, B2. So what should be B0, B1, B2, and so on, such that I will say that that they characterize the same function.
This is Padé?
No, not yet. Not yet. We are on the way to Padé. Right?
You mean the uniqueness of the...
I want a one-to-one mapping between this series and this series, such that I will be able to say that this and that are the same function. How do I do that?
B0 equal f of a, A0. Like you want the function.
Okay, I want the power series to be the same. Right? That's it. Okay, let's do something simple. Let's calculate what is the I now want to write this as power series up to second order in X. Up to second order in X. So first of all, please agree with me that I can take out all these terms, because they must give something which is at least third order in X. Okay? So I can forget about this. And so this is B naught times e to the B1 X times, but now since I'm interested only in second order in X, I can expand this to 1 plus B2 X plus 1/2 B2 squared X squared. And actually, I immediately see that I don't need even that, because this is already X cubed, right? So I can forget about that. And now I will expand this to a power series, and I will get what? I will get B naught times 1 minus B1x minus plus B1x plus B1 B2 X squared. You see? Is that the end?
No.
Why?
You need the X cubed.
I need the next term,
Okay.
right? But the next term is 1/2 times B1 squared X squared. And all the other parts of the next term are already X cubed. You see? Do you understand that? I mean, it's algebra, but right, nothing peculiar about that.
Can you explain again the motivation for what?
Let's please allow me to continue with the algebra for the moment.
No, like the first thing you said about the connection between the coefficients.
Yes. Okay. So now I can say that this series is up to second order in X. I can write it as A naught plus A1x plus A2x squared. Okay? And I want this series to be equal to this series. So this allows me to decide that A naught, which is the coefficient of x to the power of 0, must be equal to what?
B naught.
To B naught. Now, what is A1?
B1. B1, B naught.
B naught times B1, because this is the only term that includes x. What will be A2?
B
B
naught.
naught. B naught, B1, B2.
B naught, B1, B2, this
Plus
one, plus 1/2 B naught, B1 squared.
Right.
You see? Now, you see that if I have A naught, I can define B naught. So B naught is A naught. So now I can calculate B1 because I know B naught. B naught is A naught from the last step. So I know that B1 is A1 divided by A naught. Right? Let's do the calculation, right?
Yeah.
B naught is A naught, and therefore B1 is A1 divided by B naught. So it's A1 divided by A naught, right? And B2 will be A2 minus 1/2 A0 because B naught is A naught times B1 squared. So I have A1 squared divided by A naught squared. And I have to divide it by A naught times A1 over A naught. Of course, this and this cancel, and this and that cancel. Right? So you see that it gives me one-to-one correspondence, and I don't have to solve complicated equations, because in each step I have to solve, I have just to plug, because I know the B from the lower stages of the tower. So in order to have another floor in the tower, all I have to do is to take this, move it to the other side, and divide by that, and so on and so forth. Right? Of course, it will be horribly complicated if you are taking it to larger and larger powers. But essentially, the procedure provides us with a function that gives this all the curve. If I will do it ad infinitum, right, I will have a function that agree with this order by order in A. Okay? Fine. So up until now, all I showed to you is that instead of writing the damn power series, I can do something like that, right? I can write horrible function that with infinite amount of work, I will be able to calculate all the coefficients, and it will give the same power series. Okay? Are you with me? Good. Here comes the tricky point. Now let's have an example. I want to. Now I'm not going to prove you what I'm going to say because I have no idea how to prove that. But I'm just quoting results that mathematicians worked on, or who knows who. People were stupid enough to consider the continued exponential of the form e to the x, e to the x, e to the x, e to the x, and infinity. And it turns out that this is a series sum from n equals 0 to infinity of n plus 1 to the power of n minus 1 divided by n factorial times x to the n. Don't ask me how they do that. They did. Okay? So this is a power series, and this is its continued exponential representation of the same series. In what sense it's the same? It's the same in the sense that the powers are, okay. Are you with me? Good. Now, here's the question. What is the convergence radius of the series? Around 0. What is the radius of convergence?
It's like an exponent, so maybe.
Not really, because you have n to the power of n. Okay, so let's ask ourselves how the terms of this series looks like when n is very large. Because this is what is important, right? So when n is very large, n plus 1 to the power of n minus 1 is simply n to the power of n. Because 1 is very, I mean, I can write it as n plus 1 over n to the power of n times minus 1 over n, and to neglect 1 over n when n is large, right? So what I have here is n to the n divided by n factorial, x to the n. Now, do you remember what the asymptotics of n factorial? N factorial asymptotics is e to the n times n to the n. So the n to the n cancelled, right? So this is n to the n divided by e to the n times n to the n, x to the n. And this is, of course, this cancels. So I have here x over e, x I have here x over e. Am I right? Sorry. It's e to the minus n. Yes, it's e to the minus n, x to the n, n to the n. So I have x to the minus n, so I have ex to z.
Can you explain why it's asymptotic?
That's a gamma function. Still, Stirling formula. Stirling formula is that n factorial is going like e to the n ln n minus n square root of 2 pi n or something. Right? That's Stirling's formula. I forget about this. Right? And here e to the n ln n is simply n to the power of n. Right? So I mean, of course, there are also other corrections, but if I'm taking only that, I will get this. Okay? So it goes like ex to the power of n. So what is the radius of convergence?
1 over a. 1 over a.
1 over a. Right. So I have a circle of radius 1 over a in which this series will converge, and out of this disk, this series diverges. However, this continued exponential converges in wider region, right? This continued exponential converges inside this heart, right, that ended up in minus e. So they both give the same answer inside the red region. Why? Because they are the same series, right? But the continued function converges in a wider regime. That's the miracle, right?
This series can convert in any x equal to minus anything.
No, because Taylor series have a radius of convergence. If you find the point where it does not converge, then it defines a disk. Again, it's like the function 1 over 1 plus x, say, which is sum of minus 1 to the power of nx to the n, right? This series converges only between minus 1 and 1.
Yeah.
This is a perfectly kosher function that converges everywhere except at the point where, that give you finite number except at x equals minus 1, right?
That x equals
So you may think about it as a function that have radius of convergence that is better than this one. Of course, it does not have a radius of convergence. It simply give you number, right? But this is like the series, this is like the continued exponential. Have you realized, questions about this point? Okay? Fine. Just a technical nomenclature. The technical nomenclature is that we replace the terms in the power series, right? We have power series like A0, A0x, A0 plus A1x, A0 plus A1x plus A2x squared, and we replace them by B0, B0 e to the B1x, B0 e to the B1x e to the B2x, and so on. Yes? So these are called approximants, right? We replace the series to each other by its approximant, and while the series converges only here, the series of approximants converges in all this green region. Okay? Good. So this is just okay. Now our main story here is about Padé series, and Padé is simply the same trick, but not with these continued exponentials, but with continued fractions. So to remind you,
does it have any relation with analytic continuation?
sorry?
Does it have any relation with analytic continuation?
Of course, it is an analytic continuation because both functions. It is an analytic continuation because both functions are identical here. So analytic continuation implies that this extension is unique. If you are now doing not continued exponentials, but continued logarithms or continued Bessel functions, right? Maybe it will converge in a different place, but if it will converge here, it will converge to the same thing that the continued exponential converges, because it is the same function. That's the idea of analytic continuation. That if two functions have an overlap in the complex plane, then they are the same function. So the extension is unique. Okay, good. Now we are going to speak about continued fractions. What are continued fractions? So, continued fractions, again, I am starting with the sum from n equals 0 to infinity of a n x to the n, and now I want to write it as b naught divided by 1 minus b1 x divided by 1 minus b2 x divided by 1 minus b3 x, and so on and so forth. So instead of it's but right, it's the same thing, same idea. Okay, so to begin with, let's just to do something with our hands. Let's calculate the second order. So here we have a0 plus a1x plus a2x squared. Okay. Now here, of course, we need only this part because all the rest is x cubed. And I can write it as b0 divided by 1 minus b1x times, 1 plus b2x plus something x squared, but I don't need it because it will be x cubed, right? And now I expand this, so I'm getting b naught times 1 plus b1x times 1 plus b2x, right? And then I should take also plus, not 1/2, sorry, no 1/2 here, plus b1 squared x squared. All the rest is order x cubed. So what I've obtained is b naught plus b naught b1 x plus b naught b1 b2 plus b naught b1 squared x squared. So by the same token as we did before, we can say that b naught is a naught and b1 b naught b1 is a1, right? And b naught b1 b2 plus b naught b1 squared is a2, and so on and so forth. Same trick. Note that it's not in the exponentials. We have a 1/2 here, and here we don't have the 1/2. Otherwise, it's even the same expressions, but only to that order, of course. If you are going to higher orders, we got differences. So you understand what I'm doing here, okay? Okay. So this is representation of power series by by continuous fraction. Now, here comes another technical point. Are you with me up to here? Okay, good. So here comes another technical point, which is that, okay, so let's think about if I'm writing A0, so A0 will be, if I'm having A0, it will be B0. If I have A0 plus A1x, the approximant will be what? Will be B0, right? B0 divided by 1 minus B1x. You see? Okay. Now you have to give me credit because I'm going to do something that will look stupid, but what I'm saying is that this, to remind you, a polynomial of degree m, say, is I don't know, c0 plus c1x plus c2x squared up to c mx to the power of n. Okay? That's a polynomial of degree m. Just definition. So I would like to say that A0 is actually a polynomial of degree 0 divided by a polynomial of degree 0. That's an idiotic way to say that this is a constant. Okay? The approximant for this is polynomial 0 divided by polynomial 0. Okay? This approximant is polynomial of degree 0 divided by a polynomial of degree 1. You agree? What about the next approximant? So if I have A0 plus A1x plus A2x squared, I can write it as B0 times 1 minus B1x divided by 1 minus B2x. Okay? So now I can make a common denominator here, and I will have B0 times 1 minus B2x divided by 1 minus B2 plus B1 x. See what I did? Very simple. And what we can say about this in terms of polynomials? In the numerator, What? In the numerator, we have a polynomial of degree 1, and we divide it by what?
P to the degree 1.
By a polynomial of degree 1. Okay? So, note, 0, 0, 0, 1, 1, 1, and if you will calculate the next one, what you are going to find? 1 over 2. Polynomial of degree 1 divided by polynomial of degree 2. Okay? So the next one, a0 plus a1x plus a2x squared plus a3x cubed will be by polynomial of degree 1 divided by polynomial of degree 2. What will be the next one? 2, 2. You see how it works? I add index to the denominator and then to the numerator. Numerator. Okay. Now, so by and large, we can say, and now it's more, it's a little bit wider than the idea of continuous fraction. Continuous fraction. Why? Because if I'm writing sum from n equals 0 to, I don't know, p plus q, right? P plus q or p plus q plus 1, p plus q, of a n x to the n, right? How many constants I have here?
P plus q plus 1.
P plus q plus 1, because I have also the 0, right? I can write it as polynomial of degree p divided by a polynomial of degree q. Now, how many constants I have in a polynomial of degree p? No, p plus 1. And q plus 1. So I have here extra parameter. Here I have p plus 1 plus q plus 1. So it's p plus q plus 2. This one have p plus q plus 1 terms, a's. Here I have p plus 1 plus q plus 1 terms, so I have p plus q plus 2. Okay, however, I can always, as I did here, if you note, in the denominator, the first term is always 1. Right? So I have only q in the denominator. You see? So, in general, I can represent every sum, every polynomial like that, as a rational fraction, right, of two polynomials, one of degree p, one of degree q, provided that the first term in the polynomial in the denominator is 1. Okay? Now, this implies, interestingly, that I can present the following table. Now I should make no mistake because, right? I have here, yes. This is P, this is Q. So I have 0, 1, 2, 3, 0, 1, 2, 3. Right? So for example, if I have A0, I must represent it by a polynomial of degree 0 over a polynomial of degree 0. Right? Which is what this is what the continuous fraction give me, but this is the only possibility. Okay, you see? So this is polynomial of degree 0 divided by polynomial of degree 0. Okay? Now, if I'm trying to find an approximant for a0 plus a1x, I can do it There are two ways of doing this. One of them is the way I did it here, which is P0 divided by P1, but I can do also P1 divided by P0, right? So this is, here I can do it by P0 divided by P1, or by P1 divided by P0, right? Now, what about A0 plus A1x plus A2x squared? There are three ways of doing that, right? Which are P2 over P0, which is exactly that actually, right? And P0 over P2, and here I have P1 over P1. You see? And of course, if I will have x cubed, so I have P3 over P0, P2 over P1, P1 over P2, and P0 over P3, and so on and so forth. Right? Now, what I have showed you here from the continuous fraction, these are all the possibilities. I can always use any approximant to whatever order by rational function from the fraction of two polynomials of this type, right? It's very technical, I know, but there is nothing complicated here. And what I have showed you in this expansion, when I use continuous fractions, was this is B0, 0, 1, so I'm going this way. 0, 0, 0, 1, you see? And from 0, 1, I have the second order, it's 1, 1. And from 1, 1, the next one I told you will be 1, 2. And the next one will be 2, 2. And then it will be 2, 3, right? This is called the main Pade sequence. Right? Which is exactly what I'm getting from this continuous fraction representation. But I can use other things. Right? This is the Pade, main Pade sequence. Good. So up until now, I just show you technicalities of this garbage. And once we know that, we can start speak about important things. So suppose you're doing physics now. Okay? What does it mean physics? For example, I want to calculate phi double prime plus x phi equal e phi, phi of minus infinity equal phi of infinity equal 0. What is that? I want to calculate this is the harmonic oscillator. Right? Now this is a Sturm-Liouville question, problem, and we know that not every E allow for solution that satisfies the boundary conditions. Only a finite set of E's, right? And in this representation, when I took H bar to be 1, omega to be 1, half to be 1, and everything to be 1, I think that you find out that E naught will be 1/2. I don't really know. Maybe it's yes, E naught is 1/2. Okay? And now, and this is a solvable question. And we're all happy, it's harmonic oscillator. What else? If we don't know how to solve harmonic oscillator, then we can throw all physics to garbage. What physicists are doing is solving harmonic oscillator and mapping other problems to harmonic oscillator, damped harmonic oscillator, coupled harmonic oscillators, and so on and so forth. That's physics. I mean, 50% of the activity in physics is doing that. And now, suppose that I have, unfortunately, so you didn't.
Okay.
You didn't. I guess that. I mean, just to be. If I'm already at this stage.
No.
Yeah. In order for this to be 1/2.
Okay.
We are going to go to this. I mean, we are going to deal with that in the future. But now, so this is solvable function, and we are happy and so on. But unfortunately, this implies this is a pure harmonic oscillator. So it implies Hooke's law, right? You pull something, and the force, the restoring force, is proportional to the displacement. Right? That's Hooke's law. But you know that if you take a spring and you pull it too much, then it will not be proportional to the displacement. There are corrections. And the corrections are of the form phi double prime plus x squared over 4 phi plus epsilon x. The 4 is just some parameter. Phi equals e phi. Right? This is an anharmonic oscillator. Right? So we have x, f equals x minus x cubed. Right? This is this. F equals minus x minus epsilon x cubed. This is with the same boundary conditions. This is almost unavoidable. In any physical system, you have some anharmonicity. And now we want to solve this equation, this problem with the anharmonicity. And you look very, and you look at it and you find out, so the solution here is phi is equal to e to the minus x squared over 2 or something, right? And you try to find the solution here, and there is absolutely no solution. So your only way to proceed is to assume that epsilon is small and to build a perturbation theory around epsilon equals 0. This is what people are doing, right? And we didn't show yet how to do such a perturbation theory because we did only local analysis around some x, not around some parameter. But there is a way to. And then so what you really want to find is this. The ground state, right? As a function of, as a function of epsilon. You want to find what the ground state as a function of epsilon, right? So let me give you, okay. So to the 0th order in epsilon, what's the answer?
The first.
What?
1/2.
1/2. Yes, good. What's the first correction? Okay, so we are going to do that. You are going to calculate the first 80 terms in the perturbation theory. Believe me, it's not so complicated. But for the moment, I will give you the answer, right? So the first correction is plus 3/4 epsilon. The second term is minus 21/8 epsilon squared, right? The third term is plus 333/16, I guess. Yes. Epsilon cubed, and so on and so forth. Okay? What's even worse is that the terms are growing very fast. They are going like, I guess, n factorial 3 to the power of n. Right? So you have oscillations, but the terms are growing and growing and growing, and you cannot sum these things. This is a standard thing that happens always in physics. As I told you, all the important perturbation series are diverging. What's the reason? The reason is because if you take epsilon to be negative, what will happen?
So that you can go.
Right? If
you can reduce
epsilon is positive, you have something like that. If epsilon is 0, you have something like that.
You can
That's
reduce
harmonic
the energy
oscillator.
always.
Right? If epsilon is positive, then you have something that goes like that. So very close to 0, it's still like x squared, and further away it goes sharper. But what's happened if epsilon is negative? If epsilon is negative, it will win somewhere, so we will get something like that.
There's no ground state.
There is no ground state. The particle, if you start here, will tunnel out to infinity. Right? So there is no ground state. So you cannot accept this problem to have definite answer when epsilon is negative. So for negative epsilon, it's like having a branch cut on the. So and you are now trying to expand things around 0, around epsilon goes to 0, where all this line, the negative epsilon line, is a branch cut. And therefore the radius of convergence is 0. This is a generic behavior of power series in physics. Always. It goes like that. So you cannot, of course, in the course in quantum mechanics, they even do not show you how to calculate this. Because it involves a trick that they don't want to get into. So they show you 2 examples, I guess. Zeeman effect, which is a lie, because the Zeeman effect is the Hamiltonian of the hydrogen atom in magnetic field is completely solvable. Right? You can solve it by an appropriate transformation. So instead of solving it, you present as if you pretend as if you are doing perturbation theory, which is fine, but it's not a real example. This is something which is not solvable. Right? And that's why they don't show you that. Right? This is not solvable. But usually in perturbation theory, you calculate first order, second order, and then you are saying, okay, epsilon is small, so I will take only second order. But formally speaking, this series diverges for every epsilon, no matter what. So how can one calculate Z? And now I know that epsilon is 0.2 or even 5. How I am going to calculate the ground state of the anharmonic potential from this power series? That's a question. That's the mega question of physics, right? The justification for the use of mathematics to study the world, right? You have a diverging series, and you should find a way to, if it has any usefulness, you should find a way to give me the correct answer from this diverging series. You see the problem? Yes.
When will we calculate the 80 terms?
Sorry?
When will we calculate the 80 terms?
Either next lecture or one lecture after. We are going to reach it very. Of course, you are going to do that with computer, but it's quite easy. Easy after you're doing hard work in order to prepare the script, but yes, it's quite easy. So, what should we do? Here comes the fantastic answer. The answer is the only way to extract information from all those series is to padei them. You have to padei it. Right? Now, so this is a series of A0 plus A1 epsilon plus minus A2 epsilon squared plus A3 epsilon cubed and so on and so forth. Right? So you want to calculate the main padei sequence. And you see the main padei sequence is having even and odd things. The even are on the main diagonal, and the odd are on the subdiagonal, right? The even are 0, 0, 1, 1, 2, 2, 3, 3, and the odds are 0, 1, 1, 2, 2, and so on and so forth, right? So we have the even and the odd. Okay? Now, here's the nice thing. Our cousins, the mathematicians, provide us with the following statement. If this is the correct answer, right? Then, if and this is now n, right? So we have 1, 2, 3, 4, 5, 6, and so on, right? Now, so this one is P0 over P0, right? Say, right? This is the 1/2, right? Not exactly, but this one is P1, P0 over P1. Now this one is P1 over P1. This one is P1 over P2, and so on and so forth. Right? You understand what I'm doing? Okay? What you're going to get is something like that. So the Padé sequences will diverge, will converge, right? Plus the even one, Pn over Pn, that's the even one, that's the main diagonal here, will always be above, and the whatchamacallit, the odd ones, Pn over Pn plus 1, will always be below, and the right answer will be between the two. That's a miracle, right? And this allows you to take the first few terms of a diverging series, right? And only the first few terms, and to find out very good and tight boundaries for the correct answer. This is, I guess, the blackest black magic in physics.
But I don't understand why it happens. Like, why does it like converge to the...
Very good. Okay. Now, I don't understand either. Okay. Now, what do you want to say? Okay, I want to say that, just a comment. Now, if you want to do better, because it goes bang, 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 you can change it. Remember Shank's transformation? So you can change it and get it something that is doing even better. But you will see that after you will calculate the first 80 terms, right, you will see that how fast the Padé is converging. It's amazing. It's amazing. It really converges very fast. And this is actually the justification for doing physics, as I said, because all the perturbation series in physics are diverging, and you can't do anything. So you can solve only the harmonic oscillator, and that's it. But physics is about perturbation theory, because no physical object is perfect. And we always have some anharmonic corrections. And the only way we know to find out the actual ground state of the Hamiltonian, or whatever we like, with these perturbations, is to do to implement Padé approximations. Okay. Now, I must say that okay, no, let's go on and speak about conditions. So this is not an unconditional statement, what I told you. right? Because as you see, there must be, as I told you about the Shanks and the Richardson approximants, the Shanks and Richardson what do you call it? Extrapolations. It must be based on some knowledge about the series, because maybe the 10,000 term in the series is 10 to the Google, right? And you see what I'm saying? There is no way on earth that Padé will work for everything, right? It must know something about the structure of the series. And so Padé is working under some conditions, and now I would like to tell you what the conditions are. Are you with me? Good. So, this theorem that we have convergence, and that the convergence will be for the PNNs from above and from the PNN plus 1 from below, and the right answer will be bounded between the above and the below, is applicable to Stieltjes functions. So in order to implement the Padé approximation, for example, to the energies, to the ground set energies of an anharmonic oscillator, you must be a man of faith. You should believe that this function is a Stieltjes function. Now, what are the conditions? What makes a function a Stieltjes function? There are two conditions. One of them, two sets of them. Okay, a function is a Stieltjes function if you can express it as the integral from 0 to infinity of e to the minus t, of rho of t dt divided by 1 plus xt. So if you remember Stieltjes integral that I showed you in the last lecture, I guess, what is Stieltjes integral? This is a special case of a Stieltjes function. So Stieltjes integral was the case where rho of t is e to the minus t. Right? But in general, every function that has this form is a Stieltjes function, provided that two things. One of them, I want rho of t to be positive semi-definite for t between 0 to infinity. A. B, I want all the moments t to the n, which are the integral from 0 to infinity of t to the n rho of t dt, right? That's the nth moment of t. All the moments exist for every n. Right? So if the a ground set energy of anharmonic oscillator is a Stieltjes function of epsilon, okay? Epsilon is like x, right? If this function of epsilon is, if you put here epsilon, right, is a Stieltjes function that satisfies this and that, then the guarantee by the mathematicians that we are guaranteed that the Padé approximation will work.
Here n can go to infinity, right? And,
Sure.
And it's not bounded.
For every n. Every n. Now, just to give you some hint about the relevance of the moments here, you see that I can expand it, so I can write a Stieltjes function as the integral of rho of t dt times the sum from n equals 0 to infinity of xt to the power of n with the minus 1. Right? Now, this is the sum from n equals 0 to infinity of minus 1 to the power of n times x to the power of n times t times the nth moment. Right? So if you remember in the Stieltjes integral we have calculated this, and the nth moment was n factorial. Right? So this is a generic thing. And once you can write it like that, then Mr. Stieltjes and Padé and all their gang were able to provide us with this fantastic formula. Okay? Now, another aspect of the same story is that this is a condition for a function to be a function of Stieltjes. There is another set of conditions that is completely equivalent. So this is set A of conditions, and now I will show you set B of conditions, but they are completely equivalent, meaning that if a function satisfies Z, then it satisfies the other set and vice versa. Right? So the other set is, this is set A, let's call it, right? Set A of conditions, and now I'm going to detail set B of conditions, and set B is like that. First of all, f of x. Okay, maybe I should call it z. Okay. Oh, whatever. X becomes z, right? Because now this is analytic. This is something that you can think about as a function of a real variable. But now the analytic properties are important. So f of z, which is again, it's the integral of rho of t dt over zt, right, is analytic in the cut plane. That means if this is a complex plane, right, that's real z, and this is the imaginary part of that, okay, f of z is analytic everywhere except on this purple line. Right? It's analytic here and here and here and here. Only here it's not analytic. Fine? Okay. Second condition, f of z goes to 0 when z goes to infinity. Now, z may go to infinity either like that, or like that, or like that, no matter. Right? No matter how, or like that. Okay? No matter how it goes to infinity, when it becomes infinite, the function is going to 0.
Again, the complex plane is a sphere, right?
Yes. Number 3, at z going to 0, again, no matter from which side, right? Then f of z is asymptotic to sum from n equals 0 to infinity of minus 1 to the power of n times an times z to the power of n, which I've showed you is somehow related to the behavior of this integral, right? Okay. And condition number 4 is that f of z is, okay, now this property have two names. Is either Herglotz or Nevelina. Nevanlina. Double N, yes. Okay? So it has Herglotz property, also known as Nevanlina property. The property is that how do I say? The image part of f of z have the same sign as the image part of z. Right? So for example, f of z equals minus z is not Herglotz. Because if z is x plus iy, then f of z is minus x minus iy, so the sign of the image is not the same. Right? So f of z should have this Herglotz property. Okay? And these four conditions are completely equivalent to these conditions, and vice versa. So it's if and only if. Like, if this is satisfied, then the function is still just. If this is satisfied, then the function is still just. And these four conditions imply this story, and this story implies these four conditions. And as I told you, for a function of Herglotz, our cousins in the mathematics department of who knows what French universities 150 years ago, or 20 years ago, were able to show that this happens. Okay? There is only one subtlety here. Now, and also, almost all perturbation theories in physics are Stieltjes functions. Okay? Now, there is only one subtlety. What the mathematicians actually prove is that, first of all, we have the series of the even approximants that is going down to the function. We have the series of odd approximants going up to the function, and the function is bounded between the two lines, and both of them converge, right? Both of them converge, but the mathematicians did not gave us a guarantee that they converge to the same point. So essentially what may happen is that if this is the correct answer, this series will converge to here, and this series will converge to here, and that's it. And we will never know by using the Padé approximation, but using the series of Padé approximant for the perturbation theory, what's the right answer, right? In order to prove that they will not only converge, but they will converge to the same point, which must be the right point because the right answer is trapped between the two series. So in order to show that they converge to the same point, we need another property that was what's the name of this property? Yes, Charlemagne. Yeah, you know who was Charlemagne?
Huh.
Karel the Great. Karel the Gross. Yeah. Okay, so he was the king of the founder of the Holy Roman Empire. But this is not this guy. I mean, it's just the surname of the I guess mathematician that proves that. And okay. And the real have you heard once the question, can you hear the shape of the drum? It's the title of a very famous paper by Cass, I guess, in the 60s. And he asked a very simple question. Suppose you have a drum, right? You hit the drum and you hear what? Sound. But now do Fourier analysis, and what you will get? No. Do Fourier analysis.
Yeah.
What you get from Fourier analysis?
Frequency.
The frequencies, the resonant frequencies of the drum, right? If you have a guitar, right? You have a how do you call it? Metal? String, right? And you hit it, and you can hear the harmonics of the string, right? In the drum, it's more complicated because it has to do with the zeros of the Bessel function. I'm sure you have met it somewhere, and you get a very complicated spectrum. But you can do Fourier analysis, and from the Fourier analysis, right, you find out that you see that you have this peak and that peak and that peak and blah 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 blah. So you find that the spectrum of the drum is lambda 1, lambda 2, lambda 3, and so on and so forth, infinite. Right? Suppose that you hit it strong enough so that you can measure the whole spectrum. Right? I give you the spectrum of the drum. Now there is a very simple question. Can you give me the shape? So, what?
You can.
So this was a very important question in who knows what, harmonic spectral analysis or whatever, this bunch of mathematics and physics. For many, many years, I guess like 50 years, until somebody was able to solve the problem by giving two different shapes that are not topologically equivalent and have exactly the same spectrum. Right? So you can't. You can't hear the shape of the drum. But under some conditions, you can hear the shape of the drum. And the condition is that it has to do, so that the nth moment, so the nth moment, which is an, okay. So the nth moment is going up not faster than c to the n factorial squared, I guess. No, sorry, 2n factorial. It's not n factorial. It's 2n factorial.
Cn is the derivatives, right?
So, no, c, it's a constant.
Ah, okay.
Constant to the power of n, so exponential times 2n factorial. If the nth moment is going slower than that, then there is a solution to the moment problem. You can hear the shape of the drum. If it goes faster than that, then you can't. Or maybe at least it shouldn't be the case that you can. But I mean, the condition is not exactly that, but something wider. But this is essentially the story. Okay, so this is Charlemagne condition, and once your function satisfies, and this function satisfies Charlemagne condition. By the way, you may wonder, I told you here that in order to be a Stieltjes function, right, the function should behave as z goes to 0, like -1 to the n, an. Right, so it should be an alternating series. Okay? Now you can ask me, this is not Stieltjes function, clearly. Why?
It's not, we cannot
Because we start with two pluses. So what is a Stieltjes function is E naught of epsilon minus 1/2. Right? So this starts here and this is stitches. Just to okay. So this is essentially the story. I have never seen any physicist using these conditions explicitly, but you know, I'm not a real mathematical physicist, and I'm sure there are people who are doing that. For example, Carl Bender. Now, what I realized only recently, I mean, this is my opinion now I'm not teaching you, is that AI networks are actually continued functions, right? Because, let me just speak about it for a few minutes. So suppose we have a simple AI. We have here x1 and x2, that's the input. Right? Now we have a hidden layer here, and now we have an output. Right? So what it is doing, there are weights, W11, W12, W21, W22, and here is V1 and V2, say. And the idea is as follows. Calculate A, which is W11 x1 plus W12 x2 plus B1, some constant, right? And put it here. Then calculate B, which is W12 x1 plus W22 x2 plus B2, again some constant, and put it here. Then calculate D, which is V1 H1 plus V2 H2 plus C, and put it here, and this is out. The only tricky point here, this is completely linear. So this cannot be an AI network, right? The only tricky point is that H1 and H2 are not A and B, right? But H is, H1 is 1 over 1 plus e to the minus A. And H2 is 1 over 1 plus e to the minus B. And then from D, you are taking also H of D. So H output is not H. Output, Z, call it, is 1 over 1 plus e to the minus D. This is a cartoon of a simple network. Of course, in real networks, you have tons of neurons and connections and blah, 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 blah. But they are always doing this thing. Now, note that this is a continuous function. Right? You take numbers and you put them here, and right? This is a and in D you have H1 and H2 that are already right. If you try to calculate what is that, so that is 1 over 1 plus e to the minus. So now we have V1, but what is H1? H1 is 1 over 1 plus e to the minus W11 x1 plus W21 x2 plus B1. You see? Right? And now you have minus V2 divided by blah, 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 and minus C. Right? So this is very close to the continuous. This is a continuous function. It's not a continuous exponential. It's not a continuous fraction, but it's a continuous function. Now, what an AI network is trying to do, right? So, in our we are functions, right? In the following sense, that suppose we are speaking about identifying digits, right? Right? So we have digits like 1, but somebody else can write it 1, and somebody else can write it 1 like that, and someone is writing 2 like that, and or like that, and so on and so forth. Okay? Now, every such a digit may be translated into a set of pixels. This is what our eye is doing. We have a retina, and in the retina, it looks at a digit, and you have many, many cells in the retina, and each cell is either active or non-active. So you get something like that, right? You get something like that, and this is what is going to your brain, and your brain is saying 1. And fantastically enough, my brain is doing the same, because otherwise we cannot communicate. So we have a function from a set of pixels. Let's say we have 1,000 pixels. Each of them is either 0 or 1. And this is another set, and this is another set. And we have a function that maps a set of pixels into one of 10 possibilities, 0, 1, 2, and so on and so forth. Okay, this is a function. Now, what is a good AI network? It is something that imitates the function that we have. Right? So the trick is that you have to imitate the function. What are we actually doing? We show we pixelize the numbers, right? We show it to the network, which is much more complicated, but again, it has the same structure, right? And we ask, what is and if the output is not good, we are changing the W's and the B's. This is all what we are doing. We train the network, meaning that we change the W's and the B's until when I show it this, it say 1. Then I show it this one, and I'm again changing all the blah, 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 until it will say 2. And I'm showing this one, and I want it again to say 2. After 50,000 iterations of such a thing, right? The network is trained, and from now on it will associate correctly sets of pixels to the digits. So if you think about it as functions, right? We have a function in our brain, and we make sure that the AI network give identical answer in 50,000 points, right? Or whatever. We trained it on 1,000 digits. So we made sure that the AI network is give exactly the same answers in 50,000 cases or to our function, right? Now, does that mean that the functions are the same? Of course not, right? The function cosine x approximated sine x on infinite number of points when they cross each other, right? But clearly they are completely different. The fact that we were able to match a function in, I don't know, 1,000 points, right, by and large, can tell you nothing about the closeness of these functions to each other on any other point. So the big puzzle is what allows AI to generalize. Why the functions that we have at the end of the day, because this is a function, why the function that we obtain at the end of the day is indeed the function that we have in our brain. Right? And nobody knows the answer, by the way, as far as I know. Maybe somebody knows. I don't think that anybody knows the answer. It is just trial and error. The way people generate all this is trial and error. However, maybe this is a clue. Because this is a continuous function, and as we have seen in the PADEF, the continuous functions have the ability to imitate the correct function, what is given some constraints on this function. So it so happened, I believe, right, that the functions that are by the same token, I mean, like the same thing that all the functions, the important functions in physics are functions of Stieltjes, right? Then perhaps it percolates up to our brains or to the structure of our proteins and so on, which implies that one can imitate the function. I mean, by using continuous functions of this kind, one can imitate them. That's it. Fine. So these are my thoughts about AI, but I have absolutely no right to continue. Okay. Thank you very much.
Thanks.
לא, עם כל הסדרות בטבע שראינו עד עכשיו, מתנהלות כמו כן. אז גם
בסוף מה זה לא יהיה טוב?
הפונקציות של האוטוביולוגיה שלנו מתנהגות ככה.
לא, אבל הוא גם אמר אבל איך הוא עשה את זה עם ה-E0 אפסילון, שזה פלוס פלוס, אבל הוא אמר לא תראה פיזיקלי שמוכח שזה פלוס מינוס פלוס מינוס. כלומר הסט B, B3. נכון? נכון בסט B3? אז נכון E0 אפסילון לא מתנהג ככה?
איזה סט B3?
את רואה סט B למעלה?
כן, לא, אבל ש-E0 אפסילון מינוס חצי מתנהג ככה. החצי כאילו זה לא, רק החלק של התיקונים, לא החלק של האנרגיות. כן מתנהג ככה. אף אחד חושב את זה.
את הולכת? לאן את הולכת? ככה תסביבה מהתרגום.
מה?
ככה זה מוביבה מהתרגום.
לא, פתאום, אצלה זה ביראת כבוד.
למה? מה?
אני לא יודעת לשלח מה.
רוצה מחר לשתות? כן.
ביי,
נכון?
יהיו שלום.
מה? לאן?
היא הביתה, אני לוקח דברים מהמשרד.
תחזיר לטבע את מה שלקחתי. דרך שירותים
מה לקחת?
באזיין.
למה את מבריזה?
כי אני
למה
יכולה
באזיין?
לעשות קוונטים.
איזה קוונטים?
של השבוע. עשית?
לא סיימתי, לא. היום היה לי הפרעת קשב.
רוצה שאני אראה לך את הדבר הזה?
לא.
כן.
אין לי
אתם סיימתם קוונטים?
אחי, לא התחלתי.
לא מדברים על זה.
אני תקוע בשאלה 3. כן.
רק אנחנו?
זהו, שקלתי גם ללכת, אבל מה, לא ישאר פה אף אחד?
אני אשאר. אני לא רוצה להשלים. תרגול הזה.
לא, אני אעשה קונספט חדש.
שמה הוא? להשלים.
כאילו להשלים מהמערך, אבל כאילו עם איזה...
אז כאילו ספציפית פה יש בזה היגיון, כי גם ככה הוא לא אומר פעם ראשונה שהוא המערך, נכון? כאילו עד עכשיו כמעט בכל פעם שעשיתי שיעורי בית בשיטות פתחתי את המערך, מכונית, אם קראתי.
כן. כאילו כתבתי איזה פרומפט שממש מדריך את הג'מיני להעביר מערכי תרגול. ועכשיו התחלתי לנסות את זה
בפודקאסט?
לא. כאילו אני מעלה לו את המערך תרגול וכתבתי איזה פרומפט ארוך שממש מסביר איך לעשות את זה. כאילו שיצמד מאוד למערך, שיפרט הרבה יותר מהמערך, כאילו...
ואז הוא כאילו מוציא לך מהמערך קובץ אחר?
לא, הוא לא מוציא לי קובץ, אלא הוא כל פעם כותב חלק ממנו, וכאילו...
ואז יש לך מקום לשאלות.
כן.
כאילו, הבנתי.
כן.
כאילו הוא מעביר לך.
כן, בדיוק. כן. וכאילו יצא לי קצת לנסות את זה על התרגול שפספסתי בקוונטי, אז בינתיים היה טוב, כאילו, כן. כאילו, תשמע, אני מנסה למצוא דרך לחסוך זמן לסמסטר, אחי, אני לא מתבקץ על בכלל, כאילו, בכלל. כן, אני לא מצליח להתאפס על עצמי, אז אני חייב למצוא איזה משהו מחבר על זה. אז כאילו, אולי אם אני אעשה את זה ככה...
אולי. כאילו, למרות שאני לא אעשה את זה, אז יש דברים שלא צריך להגיע אליהם.
כאילו, מלומרית. מלומרית בטוח.
מלומרית קל.
במצב שאני...
כאילו קל שלא מגיע, שלא צריך להגיע. אני עדיין אגיע, אבל לא צריך.
אז זהו, ככה כאילו... אני גם רוצה. ככה גם הייתי סמסטר קודם. כאילו הגעתי בכל מקרה.
אם אתה אומר שזה או זה או זה, אז כאילו...
כן, אני מרגיש שאין לי את הפריבילגיה עכשיו. מצד שני, אני לא יודע, אולי זה יגרום לי דווקא לעשות יותר גרוע.
אתה יכול לנסות, לתת לזה ניסיון, כאילו. אבל השאלה בסוף זה באמת לחסוך הזמן. אם בסוף תשב כאילו שעתיים מול הצ'אט, ועדיין תצא עם כזה אותה כמות של הבנה.
זה גם לחסוך זמן וגם להבין משהו מהתרגולים, כי אני יושב בתרגולים, כמעט כל התרגולים שהיו עדיין, באמת בקושי התרכזתי, בקושי. לא יודע. אז כאילו זה גם ההיבט הזה וגם הזמן, תכלס. אני באמת צריך לבדוק כמה זמן זה לוקח.
וגם אם זה באמת צריך להבין יותר.
כן, כן. זה שקלול כזה של שני.
כן, בדיוק. כאילו מצד אחד אם זה יחסוך זמן אבל לא זה, לא תבין אז לא. מצד השני אם תבין אבל תשאר זה יותר זה גם.
כן. אחרי זה עולה לנו חיים.
אחרי זה? נראה לי קצת כן. חשבתי עוד ללכת גם למיכל.
הלכת למיכל? קראת?
אז כאילו קראתי בבוקר שאני מדבר בזה. אתה נשאר כאילו?
נראה לי אלך.
אתה עלה?
אתה יכול לטפל בהקלטה?
איך? תבריך אותי.
רק ללחוץ שם. איפה? סטארט רקורדינג ואז יעלה לך הודעה ששואלת אותך, אתה בטוח? משהו כזה? כן. תודה אחי.
תראה.
כן.
קורה?
בסדר. לאט לאט.
לאט לאט.
הכל יגמר.
לאט אבל בטוח.
אוקיי. למה אתה לא בחוץ?
אה?
אתה אוכל. תאבון.
תודה רבה. איך אתה?
מצוין.
חשבתי הלכת.
מה?
חשבתי הלכת.
לא.
יפה מאוד. גם.
כן. לא, פשוט אחת. עכשיו קהווי. רוצה קפה? קפה.
האמת?
יכול להיות מעולה.
יבוא, רגע. רוצה לבעוט?
So today we will learn about Padé approximation. So, but first of all, let's say a couple words about different type of approximation in physics. Also, in physics we use just in most cases, in most simple cases, Taylor expansion as a good approximation of some functions. We write it as a partial sum. But this type of approach has limitations. So the first limitation is slow convergence. The second limitation is inability to represent poles. Poles or other singularities of the function, because Taylor series itself is just polynomial, and you cannot can get infinity or poles when you are working with polynomials. And the third reason is poor behavior at boundaries. So there are limitations of this approach, and that's why we need to.
What is poor behavior?
So usually you have some radius of convergence of the power series. So, and if your x that you're interested in is really close to the radius of convergence, this series might behave differently. So, yeah. So, what is a Padé approximation? For example, we have some function f of x, and this function can be represented formally as a power series. Let's write it like this. So the Padé approximation of order m over n defined the following way. Just ratio between two polynomials, the m of x and q n of x. M and n, they are just highest, the order of polynomials. So we can write it as p naught plus p1x plus p2x squared plus etc. plus p m x m. And the same thing in the denominator. Q naught plus q q1x plus q2x squared plus etc. plus qn x to the power n. So that's how we define the Padé approximation of order n mn. So the question is, how do we usually find the coefficients of the polynomial? So we define them this way, that f of x minus the Padé approximation, so Pm of x divided by Qn of x is order of x m plus n plus 1. X goes to 0. So basically, left hand side should only have terms with this power of x and bigger. Okay. And there is a convention that we define q naught in the denominator equals 1. So this is just basically the whole theory of Padé. And the rest of the tutorial we just will practice how we can find Padé approximation to different functions, and we'll find different orders of Padé approximation. And we will compare them with normal Taylor series approximation. So I've noticed that you split the whiteboard on 3 parts, so that's why I decided to do the same way. Thanks.
It's not,
Yeah. It's easier to structure, I think. So have
it's
distinct parts of the whiteboard. Yeah. Because it's easy. I cannot control myself, and I can write like the whole board, and
Oh, really?
eventually I'm out of space. And yeah, that's horrible. Okay. So, the first example. Our lovely exponent. Okay, so we know the Taylor series of the e to the x is x to the k divided by k factorial. K goes from 0 to infinity. Okay, let's write a couple of first terms. 1 plus x squared 2 plus x cubed over 6 plus, and so on. Okay. First, let's compute the Padé of order 1, 1. Okay, it means that in the numerator we have a polynomial of order 1, so it should be q0 plus q1x, and the denominator we have also polynomial first order. It should be p1 plus p0 plus p1x. But as a so I change it. Let's write it as a wrote here. Should be here's p, here's p naught plus p1x, q naught plus q1x. But by convention, q naught is just 1, so I write it like this. And let's find the coefficients. So we need to use this formula. Okay. So left hand side we have f of x. I just write the Taylor expansion of our function. 1 plus x plus x squared over 2 plus and all the other terms. Then minus the summation p0 plus p1x 1 plus q1x. Should be order of x to the okay. That means that left hand side should have only terms of x cubed and high powers. So let's write it this way: 1 plus x squared over 2 plus other terms. I multiply it by the denominator. 1 plus q1x minus p0 plus v1x. Okay. And now what I want to write is the equation for each power of x. Okay. So for x to the 0th power, to x to the first power, and x to the second power. Coefficients between of this power should be equal to 0, right? So let's open the parentheses, multiply terms. Okay, so we have let's firstly group the terms and then write it down. So we have 1 minus p naught, right? This is x to the 0. Then plus here is 1 and we have q, right? Q plus q1, and we multiply 1 by this term, and here we also have minus p1. Okay, this is power x to the first degree, then plus this by this, just q1, this by this, 1/2, and here we don't have any x squared. Okay. We also have higher powers with some coefficients. So therefore we just now we have system of 4 equations: q1 minus 0 and q1 plus 1/2 equals 0. Okay, so from the first equation we understand that p naught is 1. From the third equation, p1 is minus 1/2. And from the second equation, p1 is just 3/2. Right? So we successfully calculated the approximation of order. Second, I think I have a mistake. Because in my notes, yeah, I missed the sign. So plus, and then here is a 1 minus 1/2 is just 1/2. Let's write the approximation of order 1, 1. So it's p naught is 1, then p1 is 1/2, so x over 2. Here is 1 plus q1 is minus 1, so minus
x over 2. Or we can rewrite it this way, which is the same. Okay. So, and we can actually now try to evaluate how this Padé approximation for the 1-1 compare it to the just Taylor expansion. So let's compare Padé 1-1 with second order Taylor approximation. So we take 3 terms up to x squared. So let's write this table. Here is e to the x minus t2 of x. T2 of x is just first 3 terms of the Taylor expansion. So as you see, just error of the estimation. Here is e to the x minus p11 of x. So, and for x equals 0.5, here is the error, this one, and the Padé for x equals 1, there is error there. And for x equals 2, error here is 2, 8, 9, 1. Here is 0, 4, 5. Okay, so and you can see that in every scale, even with the small x or with big X, but the approximation of just order 1-1, we didn't do a lot of calculations, right? It's much better than just 3 terms of Taylor expansion. And you see that it's pretty obvious why with growth of X, the relative error also increases, because if X is small, if X smaller than 1, then you do the square of it or cube of it, it becomes smaller and smaller. But if X is bigger than 1, the error increases. So good.
The 2 you put the limit, right?
Yeah. Because I cannot put it here. So yeah, there is a Padé is good in compared to Taylor with these things, but it also has limitations. Not limitation, but it's like a drawback of Padé that because of the polynomials in the denominator, you can have poles, but they are sometimes they capture the behavior of the function itself, and we will see it in the tutorial a bit later. But sometimes it produces just wrong pole. Okay, so we know that exponent is a smooth function. It defined for every x. So yeah, that's why it's one of the drawbacks of Padé expansion. Okay, so let's go to the next example. this function. So you know that you can represent this function as a geometric series. The question is, can we construct the Padé approximation for this function? And the answer is really simple, because the function itself is just ratio of polynomials. For this step, it's already the Padé approximation of itself. So, and you can show for any function. So let's write like this: if a particular function f of x is itself a rational function of type mu. Again, mu is just orders of polynomial in the numerator and denominator corresponding. So then, well, all Padé approximates of order m over n with m greater or equal nu and n greater or equal nu are identical. Are they identically equal to f of x? Let's look at the third example. Now f of x is arctangent. We also know the Taylor series of it. Did it last time. N and x to n plus 1 divided by 2n plus 1. It's just Taylor series. Let's calculate the Padé approximation of order 1, 1. So Q naught P naught plus P1x 1 plus Q1x. Okay. So again, I need to multiply the denominator to the Taylor expansion. So should be 1, 1, and minus x over 3, then plus x should be third power. Okay, 5 plus and so on so forth, and 1 plus q1x minus p naught plus p1x. Okay, let's
you have in the sum, you have a
Yeah.
x.
Yeah, like this. Yeah, thanks. So for we have only p naught, right? On the first, on the x to the 0th power. So minus p naught 0, then plus x, there is a 1, minus p1 plus x squared. And here we have q1. And that's it. Is that the same? Okay, so from this, let's write values. So P1 1. And Q1 should be also there. Okay. But in this case, we just have x, right? Which is strange. So we got only the first term of the Taylor expansion. Let's try to increase the order of Padam. Let's try to calculate. Then we will have q2 x squared, right? And now let's multiply it. So plus q2 x squared minus p naught plus p1 x. Okay. Now, what do we have? For the it's the same. Then for x squared, the same. X cubed also. Minus q1 over 3, right? And this by this plus q2.
Like q1 over 3.
The other result would be 0.
It's 1 over 3. 1 over. Again? It's not minus 1 over 3?
Ah, yeah. Because I do this. Yeah, thank you. Yeah, sure. Like this. Okay, then Q2 is 1/3. Okay, now the padel for the 1, 2 is x. Here is a 1. Plus x squared over 3. Okay. And if you study complex analysis, you know that function arctan has special points. So for z equals plus minus I, it's called branch point. So basically, then you in the complex and then you go around this point, you will get another value of the function, even though you did the closed loop and goes back to the original point, the function will have different value. So in this sense, these values of argument of the function is a sort of, it's not like a pole or a singular point, but this is sort of a special point. Okay, and our Padé approximation also has special two special points. So then x equals plus minus I square root of 3. This goes to the end. So again, it's in this case, these values of x just are just poles of the function, not like a branch point. But this can give us sort of a hint that in the complex plane, the original function has some special points. Good. And I think Nadav showed you the Padé table and the main Padé sequence, right? And you can choose the so if you go to the sequence, eventually your approximation will be closer to the correct solution. So there is a theorem of convergence. You can write it in the tutorial notes. Yeah, there are also Stieltjes functions that are useful in this analysis. Also in tutorial you can find the connection of Padé approximations to the methods of series summation that we talked about last time. So with the Shanks transformation, with Richardson extrapolation, and also how to connect. I think Nadav showed you how to connect the continued fractions with the Padé. So then you map this kind of a thing. You can match this to Padé, and basically you can do the same example but with this representation. Just two different ways how you can calculate actually the Padé approximation. we can do either this method of finding coefficients or this one. It doesn't matter. So the next very useful thing that we're going to cover is 2-point Padé approximation. So what if our function behaves differently at different limits of x? For example, x goes to 0, function behaves one way, x goes to infinity, function behaves the other way. Usually in physics we frequently see these functions. So, for example, f of x goes like square root of 1 plus x squared divided by 1 plus x greater or equal to 0. And these functions you can see it in the thermodynamics, in the statistical mechanics, and it's connected with magnetic susceptibility. So there are two limits of these functions. For example, then x goes to 0. We can write easily the Taylor approximation of this function. 1 minus x over 2 plus x squared over 2 plus and then x goes to 0. And the other limit, that x goes to infinity. Okay. Then f of x approximately 1 minus 1 over 2x plus of x equals 2 of x cubed. So there are two limits, and we want to approximate this function with Padé and we want to find the Padé approximation that will be good in this limit and this limit simultaneously, and in both cases. How we're going to do it? Basically, the same way as we did before. So let's calculate Padé of order 1, 2. So the p naught plus p1x 1 plus q1x plus q2x. So let's do for x goes to 0 first. Okay. 1 minus 1 plus x squared 2. Multiply to this plus q1x plus q2x squared minus p naught plus p1x. Okay, let's match the terms. So x to the 0 is just 1 minus p naught. Okay. Then next term. Minus 1/2 minus plus q1 minus p1 and plus x squared, right? 1/2. Then this by this minus q1 over 2. Okay, and then plus q2. Okay, we need to do the next cube. So from the x cube there is this term q1 over 2. And
Also
we need
Q2. Q2 over 2. Minus Q2.
minus q2.
Yes. It's minus x.
This by
Yes.
this, yeah. But why minus? Plus,
Yeah.
huh?
Oh, minus x. No, it's
No,
there.
this by this, right?
Yes.
This by this, it should be a minus q2 over 2.
Yes.
Okay. Yeah, so let me write the how we gonna match those two. So let's imagine that for the f of x we can approximate it. I call it f naught, meaning that x goes to 0. Okay, so we can write it as a Taylor expansion. K x goes to 0, and for the other point I call it f infinity. There's also expansion. There's a minus. So, and when we construct 2-point Padé approximation, we need to satisfy those two conditions. It's called P Padé approximation of order minus f x naught should be order of x to the n naught, and b minus f infinity should be order of x minus. So, and what is n big n naught and big n infinity? So we need to choose degrees of this polynomial the way that so let me write it space. It's right here. So we choose degrees q of x such that degree of p plus degree of q equals n naught plus n naught minus 1. And we propose matching conditions on both at both x equals 0 and x equals 2. So in our case, let's look at the n naught and n infinity. They should be in the then x goes to 0. Should be third power, right? Then x goes to infinity, and infinity should be 2. But the sum should be sum of those minus 1. So n naught is 3. Then n infinity is 2. Okay.
You choose n0 is 3. It's not supposed to be m plus n.
No,
plus 1.
I mean we can do more terms of the expansion.
No, because you choose p12. If you choose p12, it's supposed to be n plus m plus 1.
P1 2.
If you look up there, you say fx, it's pmx over qnx. It's
Yeah,
equal
some of the degrees.
yes, p12 is 1 plus 2 plus 1. It's supposed to be 4.
Yeah.
So
Now we understand that actually we need to. The sum of this is 5 minus 1 is 4, but we have the 3, so we need to add one more term. Okay, we can do either here is with cubic term or add here term, but because we know that it's better to have the same orders. Do you remember this Padé table? This. So it's better to be close to the diagonal. And diagonal has the same numbers. Okay. So let's write it like this. Let's add a square here. Okay. And let's match the terms. Maybe I need to go. Plus a2 x squared. When here we'll have also plus P2 minus. The rest will be the same.
So we need to take also x to the 4th.
Let's write it like this. 1, then minus 1/2 plus q1 minus p1 equals 0. Then 1/2 minus q1 2 plus q2 minus p2 equals 0. And here is q1 minus q2 equals 0. So here is q1 plus q2. Okay.
That's enough equation.
Yeah, but we need to use also other condition. Otherwise, it's just one point per depth. Then here we have let's P1 equals Q1 minus 1/2. We know that Q1 is Q2 the same, right? So I can match this. I can add this, and therefore P2 would be 1/2 plus 1/2 Q1 of Q2.
Why did you take the x to the power 3 to be 0? The polynomial is 1 over 2.
It's 2 2.
It's 2.
Yeah. I add this term, but I forget to rewrite this 1 2 2. But it's 2 2. Okay. Then let's try to write the matching for infinity. So now we have 1 minus half. So we know that P naught is 1. So we don't have any powers of x to the no, we actually have, because when you multiply this by this, let's look at it. So
But it's 0, right? I know, I see what you mean.
So just here is 1, then this by this is minus
over
Q1. Right? And also, yeah, it's actually
You have also the Q2, right? No.
should be squared.
Squared.
Should be squared, and therefore that's it. Right?
So Q1 is 0 and Q2 is 0. Because of that equation.
Okay. Let's write out the terms. From this we know that Q1 is 0. Then P1 is minus 1 half. And P2 is 1 half.
Q2 should equal 0.
Yeah. So actually we don't need to write other terms, right? And we can write the
What you get is F0.
F0. Let's see. So P naught 1. So in the okay, I see, yeah. So in the numerator we have
1.
no. In the denominator we have 1. In the numerator there is a 1 plus
Half.
minus
Minus half x.
minus 1 half. Yeah, exactly the f this one. Okay, then we need to take more terms. Otherwise, as we did with arctangent, right? We pick a wrong number of terms, and we got actually just the first term of the Taylor expansion. In this case, we just got this function.
But if you take another term in the F infinity, so you have another x.
If we take
No, I mean like in the 1 minus 1 over 2x, right? If we take something over x squared,
again,
the first. No.
okay.
If you add another term to the 3s, so don't you have like
Yeah.
one more term to add to the x?
Yeah, because the next
The
would be the power of
minus 2.
-2, and then we multiply this by this. Probably we will have we will have contribution to
Yeah.
this bracket,
Yeah,
this bracket, right? Okay. Yeah. Because it makes sense that if we have here free terms, probably it's better to have in this expansion also free term. So let's look at this. If okay, let's try this way. So just rewrite this thing. Then x goes to infinity. This is something small, and I can again expand it to the Taylor series. Right? So, and the Taylor series for 1 plus x to the alpha, then x goes to 0. 1 plus alpha plus x plus alpha x squared 2. Do you remember this? No? I mean, should be some coefficient on that. I don't remember exactly what is the. Because every coefficient is just next derivative. It should be alpha minus 1, right? There's the factorial, and next second one. Okay. So let's expand this. It should be 1 plus 1 plus alpha here is 1/2 multiplied by x. But in our case it's just x squared. Right? Then plus alpha is 1/2, alpha minus 1 is minus 1/2, so it should be minus 1 over 4 divided by 2, so it should be 8, and x squared, so it's x to the 4th. Okay, and then here is we can also expand this. So 1 over this. So we need to multiply this out. Minus 1 by the expansion of this one. So 1 and minus, well, minus because alpha in this case minus 1. Minus 1 over x. Okay. So right, and then the next term should be minus 1. There is a minus 2, so it should be plus, right? Plus 2 divided by 2 factorial is just 1, so just this term. Okay, now we need to multiply those. Then minus 1 x plus 1 over x squared plus 1 over 2x squared and I think by now we don't need the cubic terms, okay, so we can add this x and plus 3 times z. And actually the right coefficient here just 1 over x. Okay. So we know now that the new term quadratic is plus 3 over 2x squared. Let's look at this by this, add plus 3 over 2q. Strange. That's why you need to be very careful when you do that, because when, now I think I understand, when we add, here is second degree, again we need to look at the the total degree, like the sum of the degree of numerator and denominator is 4, right? And it should match up to this power with the function itself, right? But we only look at the up to cubic term. Okay. So, but this is right only if we don't have second power in the denominator.
If you have the second power in the denominator from the first equation in class, we have to take the 2 and 2 the 4 and another one.
Yeah.
Plus 1.
Yeah, plus 1.
Supposed to be 5.
Yeah.
We have to get the 5 order.
Yeah.
That's okay.
So, yeah, it should be also plus x to the 4
Right.
and with the coefficient of it. Okay. Oh yeah, we spend a lot of time on this. Okay, there is one more example with the logarithm, but so yeah, the main idea is to be very careful with the padé, to when you open this bracket to find the coefficients. So the first rule is to calculate till the sum of the powers. So we need, here is one more, and then we have another equation. And the next step, we calculate the approximation of a function, then x goes to infinity, and we will have other set of equations, and then we need to match them. Okay. So I don't think that we have enough time to calculate this again, but try to practice at home, and it should work. yeah, in the tutorial you will see also two physical examples. Last time we discussed, I think, last tutorial we discussed the example with the Eisen model and with the anharmonic oscillator. So in this tutorial we also have example with our anharmonic oscillator. Again, we add non-linear, non-quadratic term to the Hamiltonian and calculate the how the energy, the ground energy state changes, and in this case, ground state energy just a sum that does not converge, and we can use again the approximation to get the to assign to it some value. And the other example is with the electromagnetic scattering. You can also see it in the tutorial. Yeah, I think that's it for today. Yeah, thank you.
Thanks.
Your email, like to do a message.
You can write my phone number.
Okay.
Okay. I can write.
As a change, please don't put
קצת מגזים.
Okay.
קצת מגזים.
First I have an exam.
לא ללמוד על זה.
You have exam?
Not in
תקשיב, חוץ
Discourse?
לא יהיה לי מה
not in
לעשות.
discourse.
נטפליקס.
Can you give us
קודם כל זה גם
extent
משהו.
of the next exercise?
זה גם משהו.
Very Vegas. Questions that we can.
With serious?
Yeah.
צריך לעשות
I mean,
מפגש
I can
קבוצה עם
extend
אבי
it
ואנטו.
till the next week, Wednesday.
מה?
So I can, if it's okay, I can add one more week.
סונה.
So the next week, Wednesday,
Now
will
what
be
is
the line.
But don't put it at 0000.
Okay.
It makes me last fun. I have more than hours.
So it's
0
better to
0.
put it,
When you put 0 0, I think it's the next day.
technically it's next day, but
Yeah, but it's 0
the
0.
beginning of the next day is
0 0. It's not 54. It's 0 0.
yeah, but
It's the before that.
אנטל ונודו סונה עם
Okay.
PhD וסוגים.
I can put it 23, 50.
Yeah, it's okay, but not 0 0. 0 0 will make a lot of trouble. And if you can give us some more extra days because I might
כאילו
do
סונה
it
חדשה.
in the
היא מהשנה הזאת. הגיעה.
end of December.
הגיעה בספטמבר.
Okay. So
And
when
we got it
7.
11.
Okay.
כולם מודים?
Okay. What do you study? Physics?
I do my second dinner.
Okay, wow. So you have a big gap between first degree and
No, I'm a working person. I live in Northern Israel. North.
In North?
Bye.
Bye.
So I have just one day a week to do the courses,
Wow.
also see the lectures and just do homeworks and do the exams at the same day. Just one day.
Did the first degree in also in physics? Or?
No, I make my first degree in civil engineer and physics education. My second degree in what do you say, MBA?
Wow. It's not your first, second degree. So.
No, that's my first. And I learned physics and free listening.
Wow.
Now I
Well,
try
I
to
think
finish
it's- I
my
think-
second degree.
Yeah, I think on your first year, second degree.
Yeah, I want to do that because I don't have any time to do a lot of work.
Why
Further.
you have
I love
decided-
physics.
Wow. But I think it's really
I
hard
do
to
also
know.
most the quantum physics advanced. I do it. I do the statistic. I always read those things.
Okay.
And then now I have to do this course and another 2 courses. That's it. My thesis and my research.
You also do.
I do research now. I'm
In
trying to
what
finish
field?
everything.
In what field?
It's in plasma physics.
Wow.
It's nice.
You're working with
With Dimitri Gutman.
Gutman.
Yeah.
I know.
do with them a course called kinetic physics.
I mean, it's you did civil engineering, and I mean, what you're doing now, it's much more abstract than civil engineering, because
It's,
civil engineering it's connected to the real world. I mean,
I work in the real world.
yeah, yeah.
It's very far from it.
Wow.
When I started in civil engineering, you see such a thing, want to get something with 1x, that's it.
Yeah.
Everything is
very
simple,
basic.
very basic. It's very basic approximations.
I see.
First order. So when I started, it was very hard to expand things.
Yeah, I can imagine how. You
But
did.
it's
You did also MBA, so it's like
MBA is another
story.
word.
Yeah, of course. But,
Finance.
yeah, but in finance you also have a lot of math.
Yeah.
You can go to the specific field of finance and calculate all of the
I do a course called
stock prices,
stock prices and
derivatives.
I do it for 12 years old.
So my wife actually now she's studying MBA
Ah.
in Bar-Ilan here.
Bar-Ilan?
Yeah.
It's nice. It's nice courses. Doing the Technion, I think to do GMAT.
Yeah, I know. So you like to study?
I like this. It's nice. It's don't. This is the zone that I feel good. Not the boring things of the engineering. And
Yeah.
I have a long time in engineering. I do everything. So can I have your phone? No.
Yeah, yeah.
That's another number to say.
Okay.
You are from Israel, from here? Or just learning here for the...
No, I mean, I did Aliyah.
Ah, Sita Aliyah.
Yeah,
Okay.
Sita Aliyah.
Yeah. So my last homework, I get some help from ChatGPT.
That's okay. I mean,
No, I tried not to do that because I want to learn.
Yeah, but I mean, when you have.
But I have one question and you have 1 hour to do submit.
Yeah, and if you don't have time, I mean, the most the best approach is to set some time limit. For example, שעה, and if you don't complete the problem, you can ask GPT, but not ask like solve it to me, but give me some hint, like
I
it's
like to solve it completely, and then ask if
it's correct
or not.
Yeah,
and
that's
no, but that's last homework. I have to do that because I don't have time.
yeah. I see.
I lost one day
If you also
because of the 0-0.
do you also live north?
I live in the north. Today I
I
travel 4 hours to get here.
So not in Haifa.
No. I live in Sajur's Druze.
Druze village.
Yes.
So
Not-
like on Golan Heights?
Like?
On Golan Heights? Or? No?
No, not in Golan. It's in the Galil.
So yeah.
At Carmiel, you know Carmiel? Carmiel?
Yeah.
I live
Near.
near Carmiel, 10 minutes from Carmiel.
Is it? I think it's a beautiful place. Right?
It's very
I
beautiful.
was in a
Very
couple of national parks in the north.
And the north.
Yeah, they are like.
So,
I thought like it was February this
where
year
are you from?
from Russia.
From Russia?
Yeah.
Ah, you are Russian?
Yeah.
I think so, from England or something like that.
No. I mean, my name Dmitry.
Dimitri, yes.
100% Russian. It's
Yeah.
not.
It's
It's nothing
okay.
to do with
I have a good friend from
like
Russia.
Adam or John. Like yeah. So I was there in the north in the February.
It's
so
a very beautiful place.
Yeah, a lot of trees. Everything is green. And
I mean, Israel, everything. You have the north with a lot of trees and
Yeah.
rivers and.
especially in winter. But
Yeah.
then you have rains and yeah.
You have
it's,
some snow in the mountain or
in the Hermon? I never been in Hermon, but
I-
I've heard that you can also sometimes see snow in
Beit Jan.
Jerusalem.
In Jerusalem also.
Sometimes, yeah.
Yeah.
Not every year, but
Some year.
once in a while.
And the Hermon is every year is the snow there.
Yeah, because it's it's a mountain. But
And you have in the south the desert.
yeah,
You have everything.
you have every biome.
West you have the sea. And you have everything here.
Yeah.
Nice place.
Yeah.
Nice place. We need just nice neighbors.
Yeah, very bad neighbors. But
Maybe sometimes.
Israel can, how to say, solve
Deal
this
with it.
problem. You deal with it, yeah. Right.
No, we need peace, not war.
Yeah.
Yeah. Okay, thank you. Don't forget, no 00, please.
Just let it go.
Thank you.
Bye. Erev Tov.